All righty. Okay, I'm going to do rapid fire logs, graphing logs, I think, and I think also solving some inequalities, the type that you most likely would have to deal with next level of math. Although I think there are some inequality videos that extend the same concept of process of solution for a wide variety of calculations. So I would refer you to that from a lecture standpoint. This is just going to be, I'll put 5 problems on the board, very similar type of problem, and I'll do it like that. You pause the video, you practice, you know the drill. And then I'm going to do 5 random logarithms. Probably not, yeah, I'll probably just do one ln of x at the end, just because it's a special case. And we'll have at it. All right, let's make sure I center the video. All right, let's do the graphing of the logs first. I'm going to do 5 in a row. No lecture here. I'm just going to do them. And the shibboleth, the mantra. Well, let's see. I get this out of here. The mantra is set the parentheses to 0. Set the parentheses to 0. Set the parentheses to 1. And set the parentheses to the base. All right. In other words, if I had a base and I made the parentheses that base, we're always going to generate the number 1, which is an easy number to work with in math. If I have a base and I know that the answer is, and in the parentheses is a 1, then I'm really asking the question, b to the what is 1? I want you to know that for certain. That's a 0. Those are 2 good numbers to work with, because once you find them, you're basically going to multiply and add. Once you find it, you're basically going to multiply and add. There's your 2 points. When the parentheses is 0, it's undefined, because we really, when we work with logarithms in actual problems, the parentheses usually is the amount that comes from some exponent. All right, growth and decay. All right, talked more than I said I would. So now I'm just going to do the 5 in a row. Here we go. Keeping in mind that the parentheses equals 0, the parentheses equals 1, and the parentheses equal the base is going to be my guiding principle. All right, here we go. Problem number 1. I'm going to sketch 2 log base 3 x minus 4 plus 5. All right. I look at the parentheses. What makes it 0? 4. Well, that's the asymptote in this case. I want the parentheses to equal 1. I'm going to pick a 5. If I put a 5 in, I'm going to get that 5 out, because 5 minus 4 is 1. What do you put on top of 3 to get a 1? 0. 0 times 2 is 0, plus 5 is 5. Looks like when I make that a 1, I'm always going to get the constant. Now I want to make this a 3. Okay, it was x minus 4. Well, that's obviously 7. If I put a 7 in, I get log 1. I'm sorry. If I put a 7 in, I get 3. What do you put on top of a 3 to get a 3? A 1. 1 times 2 is 2, plus 5 is also 7. So there's a dot, there's a dot, there's your graph. All right, we'll examine that later. All right, number 2, let's look at y equals minus 5 log base 2 x minus 3 over 4 plus 12. All right, where do I look? I set the parentheses to 0. Well, that's 3. That's your asymptote. I have to have these amounts be positive. 3 makes this amount 0. Can't do any kind of growth and decay analysis if you don't have anything to look at. 0 is not a nice amount for growth and decay problems. Now I got to make it a 1. What makes it a 1? 4 times 1 is 4, plus 3 is 7. Then you should be able to put that in, and if it's a 1, then we have minus 5, log base 2 of 1 plus 12. I hope you see that that cancels this and you get a 12. So a 7 gets us a 12. Now it's going to be a little awkward here because I know this is decay. The inverse of decay looks like that. So I'll draw that in right now. 7 gets us 12. All right, now I want to get this thing to be a 2. 4 times 2 is 8, so I need 11. All right, if I got 11, then I've got this calculation. Oh, well, that's the number 1. So I get minus 5 plus 12, which is 7. 7 is lower, so I guess I'm still going in this direction. And I picked an 11 to get 7. That's our second one. Let's do a third. Let's do a third. Maybe I will do the last 2 as LNs. So y equals, how about we do 4 log base 2x over 5. Trying to make these look a little bit different, plus 3. And how about I give you a base here? Well, right now it's base 10. Maybe we should do a base 10. All right, so I'm not writing it, but you got to remember this is base 10. I've got to write something here. Let's do 7. There we go. All right, so what makes the parentheses 0? 0. So the y-axis is the asymptote. I know I'm going to get a 3 out if I pick the right number here, so I want it to equal 1. So I guess 5 halves. Is that right? Yeah, 5 halves. So 5 halves, when I plug 5 halves in right there, right, the 2's cancel, the 5's cancel, and I just get the number 1. And if I make log 1, this becomes a 0. 0 times 4 is 0, plus 3 is 3. So 5 halves get you to 3. Then I want it to equal the base. So I want this to equal 7. So 5 times 7, inverse operations. 5 times 7, 35 divided by 2. So 35 divided by 2 is going to get me 7. All right, but why does it get me 7? Let's actually plug it in. 35 divided by 2. Oh, the 2's cancel. 35 divided by 5 is 7. What do I put on top of 7 to get 7? 1. 1 times 4 is 4 plus 3 is 7. Okay, so boom, boom, boom. Okay, and we'll examine more data later when we get this down. All right, so now I'm going to change it to LN. And that's our fourth one. So what happens when we start looking at LN? 5 ln of x minus 6 plus 7. Let's work with that. There's only one thing I'm going to do differently. I don't like that. Let's make that an 8. All right, let's start with that. All right, there's only one thing we're going to do differently, and I'm not going to set it to the base. I want this parentheses to equal 3. Why do I want it to equal 3? Because I know what the ln of 3 is, and I think you do too. So that's the only thing. I'm just going to change this to a 3. All right, so what do I have here? I've got asymptote of 6. When does this thing equal 1? When it's a 7. So if I put a 7 in, I'm going to get 8. Then when is this 3? When I pick a 9, that's going to be 5 times 1.1. How are you? Which equals 5.5 plus 8, which is 13.5. Yeah, you want to be on the camera, Anna? You want to be on camera? Say hi to your classmates, or yeah, a guest lecturer here. Yeah, former student. Yeah. So if you need any help with logarithms, you go see Amma. Call her up tonight. Okay. Very good. All right, we'll see you now. So I forgot what I was doing. I picked a 9 and I got a 13.5. 9 gets me 13.5. Okay, so there's a dot, there's a dot, there's a that. And again, we'll look at this asymptotic behavior later in the term. All right, get this down first. All right, so one more log, make it as tough as I can. All right, so let's look at y equals minus 6 ln x minus 2 over 3 plus 20 there. I think I got some funky numbers. All right, so this minus sign means that the base 2.71, if I erased it, it becomes 1 over 2.71, right? Because this is really an exponent here. This is the value of an exponent. Well, this part is, right? And a minus sign involved in an exponential equation is a reciprocation. But I'm going to leave it there, and I'm not going to write it because we know it's base e. We know it's approximately 2.71. All right, so x equals 2. I know it's going to go in this direction. I'm going to make this equal to 1. So a 5, I'll put it right in the center, because sometimes the next point usually is between the asymptote and that one, quite often. So I put a 5 in, I get 0, because I get the ln of 1, right? I get the, maybe it's better I do this, ln of 1 equals 0. Maybe that's better if I write that. Over here, the ln of 3 equals 1.1. And over here, the ln of 0 equals undefined. Okay, maybe that's how I should have done that. Okay. Where was I? So 5 gets me a 20. Right? I mean, I know that when I make this a 1, I get that. I've seen that pattern emerge, so I'll just go to it. And now I wanted to get this to equal 1.1. So over here, I'll take my time with it. 1.1. Okay, well, that's 3.3 plus 2. All right, 5.3. 5.3. Might have been able to do that in my head, but at this stage, might be tired, might make a mistake. So 5.3 is bigger than 5. So let's go 5.3. And that gets me an approximation of -6 times 1.1 plus 20. Yeah, you got to do a little math. Minus 6.6, so -7 is 13, so 13.4. Yeah, that's smaller than that. That's bigger than that. That's how you do your graphing of logs. All right, so now I'm going to do 5 inequalities, the type that you might see when studying velocity curves in a calculus class. So let's say that I have a velocity equal to 2x squared, x minus 5, I don't know, 4x plus 12. And I want to know when this function is greater than 0. Okay, now when a velocity is greater than 0, that means something's increasing. All right, because velocity is a rate of change. All right, so I like to use grandma driving on Route 91. If we find positive velocities, we know she's heading north. Okay, it's because 91 is like a y-axis. In a textbook, you won't be talking about grandma, you'll be talking about particles traveling on the x or y-axis. I've never seen a particle travel on the x or y-axis. The closest I can get is a washcloth that travels on the x and y-axis, right? But I'd rather talk about grandma driving on 91. Okay, so how do you solve this? I want you to learn how to do it graphically. Sine chart, you can certainly use a sine chart. Hopefully learned that before. But this is all about odd and even exponents. X squared, if you look at it, it has a root, right? But it doesn't change signs at the root. Whereas y equals x, which is to the first power, changes from negative to positive. You get a sign change. Cubic, you get a sign change. A 4th degree polynomial, you don't. And sign changes here are everything, because what if I had a positive times a positive times a positive? Well, then that's a true statement. But one of them, if they change signs, if it changes signs, and it's only going to change signs at numbers really close to 5, right? Because I could throw a 4 in here and get a -1, or 6 in here, get a +1, where a 4 and a 6 doesn't change this, it's always positive, and a 4 and a 6 doesn't change this, but it's got a profound effect on this parenthesis. When I put a 4 in, I have a negative parentheses. When I put a 5 in, or something bigger than 5, I get a positive. That's going to affect that. All right, so how do I designate where there's a sign change and where there isn't? I use dashes and dots. All right, so we're going to do 5 in a row now. Starting now, I'm done talking. You just hopefully get some practice in here. I see a square, so 0, no sign change. 5, it's to the first power, sign change. I'll use a dash to indicate that. That's a linear factor. That's a linear factor. So -3, sign change. Now, I'm going to draw the graph. In order to draw the graph, I need to know, am I heading towards positive infinity or am I heading towards negative infinity? If you ever look at a polynomial, that's their behavior. Just think of x squared and x cubed. X squared, boom. X cubed, boom. Going up on the right. All right, so let's put a number in bigger than 5 to find out if I'm on the positive or the negative trajectory. I'll put 1,000,000 in, positive, million in, positive, million in, positive. Is a positive times a positive times a positive greater than 0? Sure is. So I know this graph looks like this. Here we go. And now I want to know when I'm greater than 0. I'm greater than 0 from negative infinity to negative 3. And I'm also greater than 0 from 5 to infinity. Okay, that's problem 1. Problem 2. We'll change it up a little bit. Let's look at minus 5x times x plus 3 cubed. Let's look at when is that less than or equal to 0. Okay, so I draw the axis. At 0, I get a sign change because it's to the first power. That I get a sign change here as well at negative 3. Now I put in 1,000,000. If I put 1,000,000 in here, I get a negative. If I put 1,000,000 in here and do the work, I get a positive. That's a negative product. So my graph looks like this. Oh, it's just a product. Well, no, this is a cubic root. Cubic root will take on that trajectory. We will look at y at a later date. Okay, so when am I less than or equal to? Well, less than or equal to negative infinity to negative 3. In other words, every one of these x values translates into a negative y value. Negative 3 also works, so I've got to put a bracket here. Union 0 is going to work to infinity. Okay, there's your second practice. Now we'll do a third one. And we're going to use this technique to solve other types of calculations because it's really easy. So now we're going to look at, how about we look at x to the third. Let's change something up here. 7 minus x, x plus 2 squared. Let's be greater than 0 again. All right, so I find my roots. Negative 2, well, that's a dot because it's an even exponent. Positive 7, that's a dash because that's an odd exponent. Odd exponent, so changes signs at 0. All right, so let's see. Let's put a number bigger than 7 in. Let's put 10 in. 10 cubed, positive. 7 minus 10. Ooh, that's negative. 10 plus 2 squared, that's positive. That's a negative product. Negative product means that this polynomial is looking like that. 0 is a cubic root, so I might as well do the Desmos thing and show you a bit of a cubic root. And then quadratic over here. That's what that graph looks like. What am I greater than? Only 0 to 7. Right? These y values, are they bigger than 0? Absolutely. All those y values are bigger than 0. So 0. X is less than 7, but greater than 0. You could have written it that way as well. All right, I forgot what number I'm on. I think I got 2 more to do. I think that was the third one. Let's try another one here. Let's try velocity equals 5 minus x squared times x plus 3 cubed times, I don't know, x plus 7. And let's be less than 0. Okay, what do we got? Negative 7, dash, negative 3, dash, positive 5, dot. Put a big number in, bigger than 5. Let's do 6. 5 minus 6, negative 1 squared, but that's positive. I think this is going to be positive all the time because of that. All right, negative 1 plus 3 is 2 cubed. That's positive. Wait a minute, I've said 6, right? I'm plugging in 6. 6 plus 3, 9, 9 cubed, that's positive. 6 plus 7, 13, that's positive. It looks like I got 3 positives. Looks like it's false, so I guess it's negative, huh? So that's that, sign change. I forgot the cubic. Heck with it, close enough, all right, because I can answer the question. When am I less than 0? I'm less than 0 for all these x's, right? Because those are negative y values here, right? Negative y's. And then same thing here to here. And I don't have equals, so 5 doesn't work, negative 3 doesn't work, negative 7. But this interval does, so why don't I use interval notation? Negative infinity to negative 7. Union. I don't worry about that number, but I do want less than, so I do want -3 to 5. And 5 doesn't work. So I got to do another union, 5 to infinity. All right, one more, and hopefully you got a little better and quicker at this. And maybe even graphing the logs. You tell me tomorrow if this is helpful. All right, so let's say we have a velocity and we want to know what grandma's velocity on 91 is positive. So let's look at minus 2x, x minus 2 squared, x plus 3 cubed, and 4x minus 7 to the 4th. And I want to know when grandma's heading north. All right, so odd exponent. Sign change at 0, no sign change at 2, sign change at -3, no sign change at 7/4. 7/4 is less than 2. Ooh, it's pretty darn close though. Why don't I make, you already started the problem, so let's do it. All right, so I put in a big number. I know it's going to be negative, right, because of this term. If I put in a number bigger than 2, well, that's positive always. That's going to be positive. That's going to be positive. So this multiplier by a negative means that I got a graph that looks like this. Again, I didn't look at the cubic roots or anything. Just got it up there quickly. And I want to be greater than 0. Well, that's good because there's too many places and stuff less than 0. And now I'm running out of breath. And I got to be in the dean's office in 3 minutes. All right, so when are you greater than 0? Grandma's heading north from 3 hours ago till now. -3. I think it's best to show it this way. So x is greater than -3, but less than 0. That's where all these y values are positive. That's what it was asking. All right, so there's your rapid fire. Hopefully it is helpful, but if it's not, let me know. If it is, let me know. I'm hoping it is. And if it is, then we'll just do it every night for homework. I'll do 2 rapid fire 5 of something that you're looking at. All right, see you tomorrow.